Hi Year 12. Welcome to your first flip learning experience. By now you should be fully aware of the Cornell note-taking system, and you're going to use it to your full advantage during this lesson. This is prep work for the next lesson with me, so make sure you do it and you do it thoroughly. Do your summaries before you get to class, and make sure you write your Q questions for when you're revising. Today we're going to be looking at the redox reactions of carbonyls and how you differentiate between aldehydes and ketones. Okay, so the specification points we're going to cover today. We're going to learn about the different reaction conditions for oxidation of alcohols, and we're going to describe how 2,4-dinitrophenol hydrazine is used. Okay, so a carbonyl compound all of them contain the C double bond O groups. Notice that we don't count carboxylic acids as carbonyl compounds because they have OH groups attached to the carbon as well. There's a pi bond between the carbon and oxygen p orbitals. They each have a spare electron, they share it over a pi bond, that gives us our double bond. There's two types of carbonyl compounds: aldehydes and ketones. Aldehydes look a little bit like this. They have a hydrogen attached to their carbon as well as another carbon, or in the case of methanol, another hydrogen. Ketones, on the other hand, have carbons attached to both spare bonds on the carbonyl carbon. This one here is called the carbonyl carbon. These R groups here, they represent an alkyl chain, so that could be either a CH3 or CH2 group. So, how do we name our carbonyls? Aldehydes, really easy. They all finish with the suffix -al. So, for example, methanol, propanol, and butanol. They're only ever going to be in the first position because it's an aldehyde. By definition, they have to be in the first position. About ketones. Well, they're very similar to alcohols in how you name them. For example, propanone, pentan 2-one, pentan 3-one, where the carbonyl carbon is on the third position from the end. Butanone. Notice it's butanone, not butan 2-one, because a butan 1-one would just be butanol. So how do we make these carbonyl compounds? Well, the only real way of doing it is by oxidizing alcohols. The product, aldehyde or ketone, depends on which alcohol you're using and the oxidizing agent. We're going to be learning a little bit more about oxidizing agents later. Tertiary alcohols, that's an alcohol whose carbon is attached to 3 other carbons, can't be oxidized for obvious reasons. Secondary alcohols become ketones, and primary alcohols become aldehydes, but they can be oxidized further to make carboxylic acids. So, as we covered in the lesson, oxidation can be represented by using this symbol, O, in some square brackets. It's a lot simpler than writing out the oxidizing agent because quite often it doesn't matter which one you use. Now, what about when we oxidize a primary alcohol to make an aldehyde? Well, we go from writing it like this in the structural formula to like this. So we've lost an H from here. In fact, we've lost 2 H's, and they've gone to form water with our oxidizing agent. We always write CHO for an aldehyde. Okay, COH implies that the H is attached to the O. And here we have ethanol becoming ethanol, exactly the same. What about secondary aldehydes forming ketones? Well, here we have a secondary alcohol, propan-2-ol, and we're making propanone. So you can see quite clearly where the water's come from. Over here we've lost both of these hydrogens, and either we've lost this oxygen or this oxygen has taken them away. It doesn't really make a difference which. And the O has double bonded to the carbon to make our ketone. Notice here we have an H next to this carbon and then an H next to the oxygen, which shows that the oxygen is bonded to this hydrogen. Okay. Now, oxidation in organic chemistry can be either the addition of oxygen or the removal of hydrogens, which is what we've done here. We haven't added any oxygens, we've removed hydrogens. Now, our aldehydes, as we alluded to earlier, can be oxidized further to make carboxylic acids. This is a two-step process. You're going to make the aldehyde first, then you're going to break the CH bond on your aldehyde, and you're going to make that a COH bond to make your carboxylic acid. Here, we've not only broken a CH bond, but we've added an oxygen in, so it's definitely oxidation. So this is the steps. Because there's two oxidations occurring, if we're writing the overall equation from primary alcohol to carboxylic acid, we have to write two O's in the square brackets to balance it all out. So this is the general equation. Primary alcohol plus 2 oxidizing goes to carboxylic acid plus water. An example of this, methanol becoming methanoic acid. 2 O's here makes 1 water, and if you look, it all balances out. But what if we want an aldehyde? What if we don't want to go all the way to methanoic acid? We need to use special equipment for that. We need to stop it being oxidized before, just after it's become an aldehyde. Thankfully, aldehydes have much lower boiling points than alcohols and carboxylic acids. So we can use this to our advantage. This is called distillation. So this is the distillation apparatus. Here we've got a flame, we've got a thermometer in the top of a round bottom flask, and this thing here is called a condenser. What that is a tube, just a normal delivery tube with casing around it that you pump water through. The water comes in here, it goes out at the top, so we've got cold water coming in and going all the way up. So this thing's going to be cold, over here it's going to be hot. So we heat the alcohol to a temperature that is above the boiling point of the aldehyde, but below the boiling point of the alcohol or the carboxylic acid. This means as soon as we make any aldehyde from our oxidizing, this is an oxidizing agent, we're going to be talking about that later, it goes up the tube, and as soon as it gets up here, it cools down and it condenses. It goes down this tube and it cools down and it condenses in here. So then it runs off as liquid and it's collected in this conical flask here. But what if we definitely want a carboxylic acid? Well, if we turn our condenser, the water tube, upside down, so it's pointing straight up, and we heat below the bottom, we just keep heating, we'll make our aldehyde, it will flow up the tube, but it will condense and then fall straight back down where it can be oxidized further by our reactants. This is a really good way of making sure a reaction goes all the way to completion and that we don't lose anything as a gas. So what's the oxidizing agent we're using? The one you need to know for your exams, and the multi-purpose one that we work for the whole year, is potassium dichromate, specifically acidified potassium dichromate. That's very important. Usually write this as this, K2Cr2O7, and then usually put slash and then H2SO4. Sulfuric acid is the acid we use to acidify our potassium dichromate. It is absolutely vital that you include this. It will not work if you don't use it. If you don't use sulfuric acid, it won't work, and you won't get your mark in an exam because they'll think you won't know what you're talking about. So, finally, how do we tell the difference between our aldehydes and ketones? They have the same molecular formula and very similar reactions. So mass spectrometry is not going to help us, and very few of the reactions are. They don't have very often different colours, they smell the same, we're kind of stuck. Thankfully, there's a few chemical tests. The one we're going to be talking about today is the use of 2,4-DNPH. That stands for 2,4-dinitrophenylhydrazine. Don't worry what that looks like, it's a big complicated molecule. I can show you on Monday if you like. Basically, this reacts with all carbonyl compounds. Only carbonyl compounds though. It won't react with carboxylic acids, it won't react with alcohols, just carbonyl compounds, and it makes a bright orange or red or yellow precipitate, depending on which carbonyl. The best thing about it is that you make these things called derivatives of 2,4-DNPH. This is the precipitate, and they're called dinitrophenylhydrazones. These are how we can tell which carbonyl we have. So, the derivatives, what's special about them? It's really easy to purify them and then make crystals out of them. And these crystals, depending on which carbonyl compound you've made them from, have a very distinct melting point to the degree, which you can then use to find out which carbonyl compound you had. Okay, thank you very much for listening, Year 12.